Okay. Good morning, everybody, to this machine learning in STEM lecture series. Today, we want to cover the basics of TM. Most of the lectures are actually really about learning the language. So if you're in machine learning, you have to understand what the people are talking about in that are microscopists. And so today it's mostly a language course, actually, really a language course in terms of microscopy. Before we start and go into the detail, for me, it looks a bit like a Pythonic approach that we are trying to do here. So in Python, you have these very sophisticated packages that are highly optimized, and you try to align and use these tools in very novel ways to get to the answers that you're interested in. And so now we try to get to the physics, to use the sophisticated tools of TM and combine them with the machine learning tools in Python. So in order to do that, you first have to know what information is available. And we have people with very many different backgrounds here. So that's why we start slow. In the next class, we'll go into much more details than what we do today. Okay, so bear with me. If you want to know more about TM, there are two main books about that. So Carter and Williams, lots of pictures, relatively easy to understand. If you try to start with something, that is a good book. Reimer and Kohl, very condensed. If you just want to revisit something, that is the fastest way to get to that. Then there's Sue and Spence. I think that is one. They have two books out. One is specialized on diffraction, and one is more general. And of course, all the simulations are very well explained, or the image simulation tools are very well explained in Kirkland's advanced computing in electron microscopy. For eels, Edgerton is a Bible. We have the third edition, so that's where you can read something. Another tool is my MSE 672 course, Introduction to Material Science. That was in notebooks about microscopy are there, and obviously they're online on GitHub, and so you can just check them out and do whatever you want to with them. So we have SAT as a software analysis tool, then a few other ones. Digital micrograph is available offline, free of charge. So that is one of the most used transmission electron microscopy software tools. Then on the other microscopes, there is Velox on the Thermo Fisher, formerly FEI, or before that, Philips. That are software packages that control the microscope and do the acquisition. And then there's Nion Swift. Nion Swift, Velox, digital micrograph all have Python interfaces, so they can be interfaced, and you can do that with different levels of sophistication. I think Gatan is actually still at 2.7 of Python, so we will see that that is not longer really supported. Very brief introduction to microscopy or history of microscopy. So there electron was actually discovered by Davison and Germer. So 100 years of that experiment is coming up. De Broglie with the wave-like character, and it was not very long after that discovery that there was a microscope. And I'm putting up this slide because in electron microscopy, the time span from discovery to commercial product is usually extremely short. And so the same thing is happening with machine learning, right? So we had the discovery of the electron, and then first electron microscope, and then very quickly after that we had the first commercial one. And then the discovery of the prototypes for the aberration correctors and the commercial product is, so it's a very fast-pacing field. And so the next I would say revolution here is probably machine learning, and we are actually hoping that you guys are all participating in making this revolution happen. So there are many of these timestamps available. I'm not sure I covered all the companies, but the most the biggest player in the fields are here for sure. So there's a difference between dedicated stems, so the ones where you have no parallel illumination, and there are timestamps. So Neon has dedicated stems, Hitachi has a dedicated stem, GOL and Thermo Fisher have timestamps, so you can switch backwards and forwards between the two modes. Another key ingredient are monochromators. Thermo Fisher and GOL both have monochromators, but they have it for Schottky emitters, and Neon has them for cold field emitters, at least at this point in time. So we can reach in the spectroscopy with Thermo Fisher or GOL timestamps. We can reach energy resolutions in the order of about 100 millielectron volt. That is what we usually use or reach with X-ray absorption spectroscopy. So we are completely in the same ball games there. Not all microscopes have that for the people not so familiar with TMs. Very novel is the one from Neon. There, people reach, or some instruments reach in the single digits of millielectron volts, and that allows you to get close to the infrared or phonon excitations. So many of the instruments are capable of doing analytical TM, so we have spectroscopy attached to them, electron energy loss spectroscopy or EDS. There are different spectrometers. The main one for eels is Gatan. Thermo Fisher is coming up with their own spectrometer, and Neon has their own spectrometer. So there is a little bit competition nowadays. It wasn't always like that. So Gatan had basically the main commercial product here. With EDS, the field is a little bit larger. Okay. So in order to get any information, so now we are back to getting information out of electron microscope. In order to get any information out of it, the electrons have to interact with the sample. Electrons interact much, much more strongly with matter than any of the or most other particles. So if you, or at least better than any kind of photons, so X-ray or neutrons specifically. So that means the sample has to be very thin. On the other hand, you have a zoo of information, and this information can be very complicated because they are interacting so strongly with sample. So there are a lot of interactions that are happening, and the most important one is scattering, and the other ones are the inelastic scattering. Now that determines how big of an interaction volume you have, right? So we come in, let's assume a single electron comes in straight to the sample. It can scatter. That means within the sample, you have, instead of going straight through here, what you do is you scatter to this side, so your interaction volumes is increasing. There is something that is called channeling. That means, and we will go into that when we do the simulation. I think it's lecture 10, something like that. So beginning of July, that's when we are looking at that. And that is actually a dynamic effect. And it's due to the Bloch waves. So you select different Bloch waves, and then the electron can scatter more forward than you would expect. The electron can interact with the atoms in the sample inelastically, so they excite some kind of transitions. They lose energy, and then at this point in time, they have lost this energy. The atoms in the sample have to go back to the ground state. They have to get rid of that energy, and they do that usually with X-rays or Auger electrons. The backscattered electrons are an elastic effect, while the secondary electrons are an inelastic effect. So if we have that, then what the key thing is for our information are actually the angles. The angles in the scanning transmission electron microscope are key ingredients, and we will talk more about that. For the interaction, we have, if we summarize that, we have mostly no interaction if our sample is very thin. So that's what we want. We want to have something like 90% or more not interacting at all with the sample. And without energy transfer, that is elastic scattering. Okay, so we have kinematic and dynamic diffraction here. So it's no energy transfer for these two. And then the inelastic scattering in an image or in a diffraction pattern would be a kind of a gray background, more or less homogeneous, but with a slight decrease to higher angles. But that is the one that we're using for analytical TM, this inelastic interaction. Okay, so we have for the elastic part, we have quite a few of different modes in the TEM or techniques. And many of them, basically all of them, are used also in scanning transmission electron microscopy. And so don't be surprised if I go over many of the ones with parallel ones, because we will see how these two things really are always happening. So if you think you only have to know about the scanning transmission electron microscope, I have to disappoint you. So we actually learn from both sides here. So if we do the different modes of a TEM in normal imaging, we are in a parallel illumination, right? So most manufacturer calls it TEM, and the objective is so the illumination is that should be condenser here. So we have different modes here, and we have actually only a few different parts of the microscopes that we are changing. The electron microscope on most instruments on the top, in a dedicated stem on the bottom. Maybe more manufacturer will change to that. That is the gun area. So we have the source, a few lenses here, monochromator possibly. And where we usually start our optics is at the differential pumping aperture after the gun part. That's where we have to get all our electrons through. So this is where the optical path starts. And of course, it ends down here at the detectors, whatever we have down here. We switch from spot, so from scanning transmission electron microscopy to TEM with the condenser lenses. So they make just the illumination. Either it's parallel or converged. The convergence angle is given by the condenser lenses and the aperture here. And we have different options. We don't worry about it. All we want to know is which convergence angle do we have for machine learning, right? So the rest we leave to the experimentalist. So that is the illumination. Then we have the objective lens that can be on or off. For low magnification, we usually switch it off. For usual in the large view, and for magnetic imaging, we have to switch that objective lens off, because that's where the sample is, exactly in the center. Okay, so that's where we are. Then from there on, we have the next important one. That is the first of the projector lenses. That is used to switch backwards and forwards between diffraction and image. So either it is in diffraction. Am I in the right place here? Okay. So yeah. So we have diffraction or imaging mode here in that first lens. And after that, we do all the rest of the magnification. It's also important in STEM, because now you can change your camera length and you have your high angular dark field detector. In this case, it's here. So if you change the angles, so you can compress the diffraction pattern, your angle for the annular detector, the angles that reach the angular detector are larger. You expand it, and it's getting smaller. So you change that there. So that's the inner angle of the angular detector. And in our case, we have now an energy filter. The energy filter can be in the column as it's shown here, or it can be on the bottom. That is at most of the microscopes with just one magnet that is bending the electron beam. That is relatively easy to understand. If you bend the beam, the fast electrons get bent less than the slower ones. And so you have sorted out your electrons by energy. We have other sorting mechanisms. In the diffraction plane, we have sorted out the electrons by angle or momentum. And in image plane, we have them sorted out by the spatial interaction. So we have different sorting algorithms. And so in STEM mode, we combine the angular one and the position. So we have a beam at a certain position of the sample. And we are in diffraction mode. And then we have both of this information simultaneously, which is the 4D STEM, which we also talk about in this machine learning course further on. Kevin is going to do that. Okay, forgot one detector. We have the objective lens here. The electrons come from here. And so in a modern electron microscope, your so here's the sample. So below this upper part of the objective lens is the energy dispersive X-ray spectrometer. So it's just the silicon detectors that are sitting around there in a circle. Okay, so this is our microscope. And depending on which button we choose, the computer puts a certain set of currents to the different lenses and switches our microscope around. So depending on parallel or convergent, whether this objective lens is on or not, and depending on where the first projective lens is, we have an image or a diffraction, and then we can, in our microscope, switch between EELs and imaging, and you can do the same thing in a Gerd image filter. It's the same thing, but it happens obviously after you have the, go over here, after you have the electron sorted out by electrons, so after the energy dispersive plane. So you can you choose that to select things. In the Gerd image filter, they got much simpler than when I started. The simplest one is actually the one in-column filter, as we have it here. I don't think our students know that you can take a diffraction pattern without an energy filter. So that shows you how the field progresses. Okay, so diffraction and imaging, that are the key things we are talking about it now. The diffraction is directly a result of the interaction. So atoms get scattered or diffracted depending on whether you are in the particle or in the wave picture. Kinematic diffraction, independent of what kind of theory you use, that gives you the angle. And that angle will not change independently of how often you scatter. So that are the Bloch waves that are excited. So that are the angles that can happen in your sample. And in dynamic theory, that means we have multiple scatterings. So it scatters and it scatters again, all of them elastically. And that changes obviously the intensity in the different beams. So the one beam gets scattered and then it loses energy, it gains energy. So the intensity is different, but the position always stays the same. So if we have a diffraction pattern and we don't care about what kind of intensity this Bragg peaks, or in STEM images with the convergence angles, the disks, the pattern in the disk, what they have, then we can just use all the normal kinematic scattering theories that we're used to in X-ray diffraction And of course, we use all these methods synergetically so that we get an answer. Neutron scattering. Okay, so from diffraction to imaging, this is in first order only a Fourier transformation. So we go from reciprocal space, momentum space, to real space, and the transformation that does that is the Fourier transformation. We will do Fourier analysis today on our samples, on our with our notebooks, and so we'll see how powerful that is. Of course, everybody knows that, but we also want to make it convenient and easy to use, right? So what do we get from that? We'll get how many beams were diffracted, contributed actually to the information that you got. The image depends highly on what kind of intensity is in the Bragg peaks. And so that you cannot know a priori. And so you have to do some image simulation. We'll do some of that. In STEM, it's a little bit, different problems with that. So whatever you do, the first thing that happens is a diffraction. And then you get an image, either by doing a Fourier transformation in the Fourier optics of the transmission electron microscope, or by using a spot and using the diffraction pattern there. So the diffraction is the key of that. And if you don't understand diffraction, you throw away 90% of the information, right? So we really have to talk about diffraction. The diffraction is also dependent on how the inelastic scattering goes. We saw already it changes possibly your volume. And the primary energy loss will give you all the transitions that are possible in an electron microscope. Here is one, it's a very old one. So, but we have the zero loss peak, that is the strongest peak, hopefully. If it's not, throw away the data, please. Okay, so we have this zero loss peak. Oh, okay, I shouldn't say that actually, because if you do momentum resolved EELs, your zero loss peak will be there. So under normal conditions, you should have a very strong zero loss peak. And that are all the electrons that are not scattered or not scattered at all, have no interaction with the samples, that are elastically scattered. And depending on your energy resolution, so if we are talking about a normal microscope with up to 100 millielectron volt resolution, then also the phonon scattering is in here. Okay, so that are the quasi-elastic electrons. This little bump here, that is the strongest inelastic scattering in a bulk material. So that is a bulk plasmon. If we extend that up, then we see we have this peak here. We will talk on Tuesday about how to analyze that. So it's a plasmon. It's a collective oscillation of the valence electrons. So give you a lot of information about your electronic structure, number of electrons, Fermi velocity, all kinds of stuff can be read from that. Before that is actually very, very tiny is where the optical spectrum is. So you can get optical properties from that. And the electronic structure. It's a very strong interaction and it's heavily underutilized. So that's where machine learning can definitely make a big impact. On the tail of this plasmon peak is this core edges. So it's sort of like edges from excitation of core electrons up into the first free states without the conduction bands. And the area under those edges give you the composition. The position of them give you what kind of elements are in there. And the shape of them give you an idea about the bonding. Okay, so if you're not familiar with a specific element or an element in a material, then of course you don't know that, right? So you would resort to doing some density functional theory calculation to get to that. We will talk about that on Tuesday. On the other hand, if you're looking at silicon dioxide like me for 20 years, and you know immediately, oh, okay, that is silicon in non-oxidized state, right? So we do it with human pattern recognition, and again, a lot of things can be done with machine learning in that range. So again, we have no energy transfer, we have little energy transfer, that is the low loss region. So if somebody talks about low loss, and you know now what it is, and the high energy transfers. So this is really not very clear cut. 50, 70 EV is a ballpark number. So it depends highly on what kind of material you have. If it is less than, let's say, 50 electron volts, then they are not really longer core states. So they are semi-core states or almost core states. So they behave then a little bit like a valence band and a little bit like a core state. So it's a bit tricky at that point then. But if you're 70 EV and higher, so you can look at them as core states. And so the advantage of that is this is more delocalized from the primary interaction point of view, while this one is really on an atomic level. And so you can get your chemical composition and your bonding very, very localized. So it depends now on the physics of the interaction, not longer on the where the interaction happens. The secondary processes, as I said, the electrons have the atoms that are excited have to go back to the ground state. This is different from any other excitations you might know about. And the reason is we don't have so many electrons. The amount of electrons, or the average time difference when an electron hits the sample, is actually larger than how long this excitation lasts, and the atoms go back to the ground state for most materials. So you can expect that your electron always sees a sample in ground state, right? So, but if you do it with optics, you have a laser, high amount of photons are hitting this sample and have all kinds of effect through that. This does not happen in an electron microscope under normal conditions. So the dynamic TEM is a bit different, but I'm talking about normal one. And then you have to run it in STEM mode, no dynamic TM can do that so far, I think. Anyway, so it has to fall back and it gives out the X-ray, and we can look at the energy of that. So energy dispersive X-ray spectroscopy. Big progress has been made with the detectors, the collection angle of the these X-ray photons. So we have now atomic resolution EDS that we can have together with eels and an image. So the key thing is we collect more and more information simultaneously with our microscopes. Auger spectroscopy is not used in a TEM, and cathodoluminescence is used very little. So that is the optical photons that come out after we have that excited. This is certainly still in its infancy. It's used much more in the SEM parts. So in a TEM, we don't use it that much. So it's a little bit esoteric. Again, this will change. The easier it becomes available, the more it's going to be used. And then I hope in the next few years, we will see more of the different techniques or the different signals being collected. And then we have to figure out how do we combine them, right? So that's what we do. Okay, let's see whether we had any questions here. How do I do that? Let's see whether we have. Aha, okay, there are a lot of things in the chat here. Okay. How is the chat going here? Tell me, what is the physical intensity corresponding to a peak in eels? Yeah, okay. So it's an excellent question. I would refer you to Tuesday, where we talk about that in detail. So the intensity of a peak or of a signal in eels is, of course, the cross section. So it's the probability of exciting any transition. Okay, so, and that is the key. So who was that? Hassan? Okay, you're on track here. You did. Okay. So yeah, so deconvolution, FFT, we do it in the notebook series. Okay. Okay, Sergey answered most of my the questions already. Okay, so
it's a teamwork.
Yeah, STEM EDS. You can use hyperspy in microscopy. I'm working on that so we already can read all the EDS spectrum images and EDS spectra. If you look in the MSE 672, there is an EDS spectrum part. So it talks about all the different features and how you model those and how you use then that for quantification. There is interesting, in my opinion, interesting development going on a few years back. Pete Nellist, so he combines eels and EDS. Eels is the primary mechanism for the signal, and then you have a yield from that with the X-rays. So lots of things are going on there, and I hope we get a lot of progress there in the next part. Okay, did we have any new questions? Apparently not. Okay, so we'll go on a little bit longer here. I just wanted, I'm droning on here, and I'm not sure whether you guys are still with me or not. So I was making here pace. When do we use electron microscopes? The answer is simple. When you need spatial resolution for your problem. You don't have enough. You want to see any kind of differences. So you have a nanoparticle, and you have all of them are the same. Go to X-ray diffraction or whatever, X-ray fluorescence. If you want to know whether a single particle is different, then you have to use electron microscopes. Okay, I'm always forgetting the scanning probe microscopes, and I'm not sure why Sergey didn't yet kill my picture here, my transmission here, but anyway, so SPM is a different animal, and of course you can also get atomic resolution here. Scanning probe. What are the drawbacks? One drawback is certainly that you need very thin specimens, and that is an art by itself. Usually needs to be self-taught. With the advent of nanomaterials, nanomaterials are easy, right? So you just put them on and you're done. But the sample preparation of anything more bulk-like is a challenge. And I would think it is the best, the biggest one in transmission electron microscope. So that's why our data are usually not optimum, right? So sampling, we are not investigating a lot, but again, that is where machine learning can help. We have electron beam damage. That is usually dose related, and so controlling dose and the amount of incident electrons, and when it does something, is a key thing in quantification. And the the electron microscopists in biology, they are much more advanced on that than we are in material science and physics. So again, something you can combine. The data analysis is not untricky due to the strong interaction of the electron with the materials. Single micrograph is only a projection, so lots of artifacts can happen here. You have to do some image simulation to be sure that you can trust your data, but it is not only disadvantage, because if different techniques converge, then your confidence level in your results goes up immediately. So that's actually, I think, almost an advantage. And PMs are, the funny thing is, the biggest challenge for new users on an electron microscope is how to put the sample in, because of the vacuum issues. They are relatively fragile, so you have to know what you're doing in order to not do something bad to the instruments. And so there is some expertise needed to run them and to set them up. But the key thing is, in electron microscopy, running the microscopes will get easier and easier. So the key, in my opinion, is to set up your experiments so that it matches your questions. And so that's where the expertise in the future will lie. And machine learning can actually help with that, because if you just get always all information and sort it out later, that is, of course, beneficial, and not necessarily you always make a good choice in the first time you look at a sample. We talked about that already. So we have scanning, dedicated scanning transmission electron microscopes. We have TEM stems. So people are familiar with that. And we talked about the different techniques already: diffraction, imaging, and analytic TEM. So anything to go. And so the key thing is and remains, what techniques do you use? How do you set up your experiment to get the right answers? And machine learning has a big part there, and we will hopefully get some advances on there. So we have a lot of techniques, all of them very powerful. The TEM is used in solving problems. So we want to understand how the atomic structure of a material influences its macroscopic properties, or quantum properties nowadays, of course. And don't use the TEM by itself, right? So I think another key component in quantitative and future microscopy will lie in the correlated techniques. So you do several techniques, and only if they match, your confidence level will increase. So that is okay. I left that part out from my lecture, so sorry. Okay, so why do we use the electrons? We have an extremely small wavelength. So in principle, you can resolve anything. So it's only determined by the instrument, so the aberration of your microscope. And the other one is why we use electrons is because we have lenses. So ions and electrons are charged. So that's why we have magnetic and electrostatic lenses for them. And so we get atomic scale imaging. So how does a TEM look like? Well, it's a stack of lenses. Well, we are used to microscopes, right? So all stack of lenses. We start with the electron source. We have different sources. They change the coherence of the electron beam, the energy distribution inside the beam. We are actually only interested in how much in the stem does arrive at the sample in what small diameter, and that is called brightness. So we are interested in brightness, and we are interested in the energy distribution within this electron beam. The beam is formed and the information is formed by the electromagnetic lenses. We have an accelerator that gives us the wavelengths. Any kind of physical interaction is dependent on the wavelengths, so we will need that. We have magnetic and electrostatic deflectors. So what we need to do is, of course, we have to scan an electron beam. So we first deflect it, then we deflect it back. So we have a spatial change. On the bottom, we have to do the opposite to get it back in the optic axis of the microscope. Optic axis of the microscope means basically the electron optical middle of the lenses has to be always established, and that varies a little bit from day to day. So electron microscope has to be aligned. That means we, with deflectors, we try to get through each lens on the optical axis of the lens through the microscope. Then we have aberration correctors. The simplest ones is just a quadrupole. In that case, if you think of a beam and you have, let's say, 2 pluses, 2 minuses, right? The electrons get attracted to the pluses and will be repelled from the minuses. So you can see it gets something like an oval-shaped electron beam at that point, and of course you can make it back. We will talk about aberrations, of course, in the imaging part. That will be the week after next in the Röntgen. Short overview, we did that already. Key thing is all we need to do to go from our beam shape to a convergent beam electron diffraction pattern in STEM is change the intermediate lens. So we will talk about that a little bit more now. And that is actually easily possible with ray diagrams. Electron microscopes are usually produced in under focus. So it means the focal point for the electron beam is below. We have a perfect Gaussian focus. So then we are perfectly in focus, and we are over focused in on that side. So that is the convention of how we are using that. So I told you it's vocabulary. So that can be, of course, played around with. There is a notebook in my introduction to material science. The idea is very simple, right? So you a lens will just make a deflection. So the lenses are used to change the illumination. Illumination is basically magnification of the source. If the source is infinitely far away, you have a parallel illumination. If the source is demagnified, then you have an electron beam. So you can also look at that way. We switch the modes. We select the angles. So as I said, that's going to be the key things that we are want to take care of. So it will go for any of the different information. It's all angle dependent, okay? And the apertures are used to select the information that reaches the detector. And that is important when you analyze it. So you need to know what you did and what kind of information is at all in your data, right? If we filtered it out before, there's no point in looking at them. So I talked about the convergence angle. In diffraction, and the STEM mode is in diffraction. So we have a convergent beam. The diffraction pattern gives us all the information that we need. If we come in parallel, the electrons are scattered in very distinct Bragg angles, and they would be in an ideal point world a spot with aberrations that are small disks. If you now increase the incoming angles, then this angle will be shown in your diffraction point, right? So it will slowly up and will become a disk. It means there is no difference in the diffraction pattern of convergent illumination or parallel illumination in the position. And so if you look at the distance between two disks, you get the interatomic distances from that, you get the symmetry from that. There's no difference whatsoever. In the dynamic, we have a large difference, because here then we have actually a map of the excitation error. That is something we are going to learn in diffraction and look more into that, because it is the most precise diffraction technique out there, and so we can utilize that, and we will utilize that in 4D STEM. Going back to the ray diagram. So, looking, it's funny. So we have an object, we have our lens, and if we go straight through, this is our optic axis, goes straight through the middle. If we go in an angle, this will be sorted out in the back focal plane here. So all the angles in this directions meet here, the angles in the other directions meet over here. So this is our back focal plane, and we have a momentum resolved electron information. So that's our diffraction. Yeah. Then in the image plane, which is a Fourier transformation, we are back in image mode. In here is also convolution for imaging. So we usually put all our instrument characteristics and convolute them when we go from the diffraction pattern down to the image. The electron microscope is unique because we have magnetic lenses, so we can change the back focal plane. And so from the object to the image plane will change. And so we can change things around here. The magnification is given by difference from the image plane to the object plane. So the back focal plane connects them too, right? Obviously, this is reciprocal formula over here. Just wanted to say something else here. No, okay. So it's interesting that you have an electron that is actually accelerated with 200 kV or 300 kV, 60 kV, whatever you use. So you are in the order of 3/4 of the speed of light, and you hit the sample, but everything is still available through the simple ray diagram. So here we have them sorted by angle, and spatially we had them already sorted by energy with a magnetic field. So we have our diffraction, elastic diffraction. That's what we were. So after the sample is, in this case, of course, whatever is coming out of the object. Yeah, that's what I wanted to say. So the key thing when you put it sample in the electron microscope is that this back focal plane of the objective lens is at a very specific plane, because that's where we have an objective aperture where we can select then whatever angle we have here. And so that's why you have to put it to a very distinct position in the height, right? So you adjust the height, and that is only due to the fact that we want to have the back focal plane with respect to the object here. It's a right place. Everything else would not work generally. Okay, so kinematic diffraction. So the position is okay. The dynamic one will show us what kind of intensity we have here within a disk or within a single spot. Doesn't matter. It's an angle dependent thing. So we go with Fourier filtering. We do Fourier filtering in a moment. We had this question, and so if you do a simulation of any kind of technique, what you really do is you do a diffraction simulation, and then you sort out where it comes through Fourier transformation or placing your beam there. Okay, so the difference between dynamic and kinematic theory is that basically you can just go to the point where you say, well, if I know where the bragg peaks are, I can do kinematic theory with it and intensities or dynamics theory. So it's multiple scattering events. These multiple scattering events in the dynamic diffraction can happen on a single atom. Okay, so if you have very heavy atom, whatever, uranium, plutonium, or any of the other very heavy atoms, a single electron can scatter twice on this single atom. There is a certain chance for that. So even the thinnest sample will have a certain amount of dynamic theory. So you cannot ignore it. Okay, maybe in graphene, but well. Okay. So the dynamic theory, the amount of electrons are given in your experiment, but depending on the thickness, it will change backwards and forwards. And then the dynamic theory can be solved only for the two-beam case, so that is a conventional TEM. Everything else really needs simulation. I have a few buzzwords, so that will end our language course here. The key terms here are scattering factor, it's normally a small f. Form factor, forbidden reflections, doesn't have a name, of course, they're not there. Cross section, so we'll talk about that more in EELS and in imaging. So, of course, right, all of that will be used and explained many times. Partial cross section and mean free path. We want to know what it is, so we have the scattering strength of a single atom, so that is a scattering factor. The form factor is when you combine them in a certain symmetry. Okay, and it means some reflections are forbidden, so it means say we're interacting destructively or interfering destructively, one should say, and so you don't get anything of that. Then the cross section is just a probability. You can express it in many different ways. Usually in diffraction, it's expressed in virtual size, and so it's measured in barns or in atoms in per square nanometer or square angstrom, whatever you want to use there. Barns is much lower than that, so it comes from the neutron scattering, I think. Anyway, so then partial cross section is what is the probability to get into diffract into a certain solid angle, and the mean free path is another measure of the cross section, right? So it's just a different measure of the probability of scattering. It's just how often or what path can an electron or particle travel between two scattering events. In dynamic theory, we have a few more. Let's just directly go in there. So we have the Bethe theory. Bethe, Hans Bethe, developed that in Cornell. He was calculating the dynamic theory as the first one from quantum mechanics. The solution to that are the Bloch waves, and we will talk about that a little bit. And the Bloch waves are directly related to your Bragg peaks. So, okay. The rocking curve is intensity variation with a thickness in this Bragg peaks due to dynamic theory and beta theory. And the extinction distance is how long does it take for a beam to for an electron beam, we need several of them, to go from one Bragg peak to the other. So basically, it's one period of the oscillating intensities in the intensity. So the dynamic theory is thickness dependent. It means you can determine the thickness. If you have an area and the thickness, you have your volume, and then suddenly you can do volume specific things. Okay. We are going to use Bloch theory in a form that is done by Howie Wieland, R.G. Howie. I met him in the Cavendish lab, so he's a fun guy. So we have the two beam conditions. We are not gonna go into that. We are using two beam conditions even in STEM imaging. Gives interesting results. So then we have dynamically activated reflections. If Bragg peak is kinematically forbidden, but you can scatter from one peak to the other, and you go back into this forbidden reflection by double, 3, 4, whatever, multiple reflections, and you're in dynamically activated reflection. Say Howie-Wieland equation, or together with multi-slice theory, we do that in the simulation. And the Fourier coefficients, or the eigenvalues of the beta theory. So they're related to that, and we get the intensities from that. So that are the basic terms that I wanted to go over with you, so that we are all on the same page. The next thing to do is I all want you to go to the web page of our machine learning course. We are in lecture 2. The slides are all here. Should have said that ahead of time. Nobody asked, so I assume you all knew that. And we want to use the first notebook. What we do is we just click on that, and then we use this button here, and it will open in Colab. Okay, so I want to talk about the mathematical description of an image in this point. I don't need much. All I need is something to plot it. So matplotlib is already there, and I need a numerical library. And we run it. Okay, does anybody have problems? Oh. Okay, I just saw that we have some questions here. Let's get back to that first before we do anything here. Gives you also time to check on that. The architecture. So the difference between TEM eels and I'm standing in front of it. So that was here. So the difference between TEM eels and STEM eels is actually the convergence angle. In TEM eels, the convergence angle is 0, and the collection angle is usually in the order of 100 milliradians. So that is an angular distribution of what you're looking at. In STEM, if you have an aberration corrected microscope, your convergence angle is in the order of 30 milliradians, and your collection angle is in the order of 50 milliradians. If you do it right, if you do it wrong, it's too small, and your results will be crappy. That happens. Sometimes, for one reason or the other, you have to do that. But say analysis is then difficult because you don't know exactly what contributes to your signal. So in TEM eels, it's relatively clear cut because you know what your convergent collection angle is. In STEM eels, you have to look at that, but in principle, they are the same from, say, angle point of view, if you convolute it correctly, which we will do on Tuesday. In STEM eels, yeah, so it's convergence angle, and so we'll handle all of that. Also, the second question will be handled on Tuesday. L3, L2 ratio. I'll show you a very, very easy and neat trick of how to get to that. Okay, so it's with a model-based analysis of the eel spectra. It's quite straightforward. Say oxidation states. I can now that I know this question, I will add something about that. Okay, but we can definitely not easily look at the oxidation state, so there is a lot of problems there. But okay, so lots of eels questions. So okay, so everybody look for the eels lesson, and I'll handle that. If I don't, remind me, and I have it somewhere. So we running this. So what we need to do in Google Colab or in any notebook, we first have to load the packages for the ones that are new to Python. And now I want to make an image. I want to, I'm over here. It's 8 by 4, right? And if we are doing that image, I want to just run this here. Then I get the way it is internally represented, and it's a matrix. So an image is a matrix, and that's it. But there is a pitfall. Because if you plot that image, so here we only use the numerical library. Here we use matplotlib. Wow, where did it go? Here. I wanted an 8 by 4 image. And if I say that as a microscopist, I want to have it 8 in X and 4 in Y. And you see the problem. The matrix doesn't do that. So there is a convention clash. One is the microscopist. And the microscopist wants to have the x-axis to the right and the y-axis up, or actually down from top right, top left down. So that's where our origin normally is, on the top left. And mathematicians have a very different view of that and say, first go down, then right. So we have two different ways, and NumPy, of course, goes with the mathematical view. With and the reason why that is important in STEM, so if you have a normal image, take your image, right? So with your cell phone, take an image. Who cares what is left and right? Oh, okay, well, so I would do like this, but okay. Independent of that, for normal scientific data, it doesn't make a difference. However, in STEM, it makes a difference. You start on the top left and you jump around. Let's assume we have 1024 1K by 1K image. then just order of magnitude we use for each pixel 1 microsecond. Then going from this pixel to that pixel is 1 millisecond. So 3 orders of magnitude difference in the time scale from pixel up, also on top of each other, versus the one left and right. And any kind of instability, of course, will be important. Most images are square. And so it's not easy to determine whether you have a problem with your scan or not. In microscopy ecosystem, we try to be as consistent as possible and have always the slowest one first. Oh, okay, that is what NumPy is doing. Oh, okay, nice. So if we have a stack of images, the stack is the slowest one, so that will be the first one. So it's also convenient because you can just say image stack 0 is the first image. And then X, Y is always the same direction as well. So if we plot them, we have to, however, change it over and say mathematical solution for that is to do the transpose. So we always plot the transposed image, and that way we will get our image the way we are looking at it. What I see very often in machine learning algorithm and so on is they don't care about the scale. That's a problem, especially if you want to look at strain and other things. So please don't do that. Make sure that your scale is correct. So if we do a pixel, and I made 1 pixel, 4 in X and 1 in Y. So you see it still works. Makes that a little bit brighter. And I go from 0 to that pixel by plotting it this line here. So it's just plot 0, 4. So that is the x-axis. I go from 0 to 4. And I go 1 in the y direction. And I make little dots in there as well. So we add a scale to that. So it means the x and y direction are not longer in pixels. And I do that here in this part. You can use any scale you want to, obviously. So we just multiply the shape with that in the field of view. So we have so and so many pixels times the size of that pixel. And that gives us the field of view. For digital data, it's the only sensible thing to do. Either you define your pixel size, or you define always your pixel size, and then you tell people the field of view. And if you just multiply your, that is called in matplotlib the extent of an image, right? So you just say the x-axis goes from our case 0 to whatever the field of view is, and the y-axis as well. So we do that, do the same thing as before. We see our line now is from the corner of the pixel to over here. And that is now a convention that I don't like. However, everybody is different. Maybe you like that better. In microscopy, we are using the convention that the center of the pixel is where we are. And again, if you want to do sub-pixel accuracy, you need to know that, obviously, right? So which convention was used? So if we start with, instead of 0 over here with half a pixel size, negative, then we have it in the center and we go to the. So again, in microscopy, this is the convention we're using. And I don't know what convention HyperSpy uses or any of the other ones, and they might change it backwards and forwards. So just be aware that there are conventions on that, and that might mess you up if you're doing any kind of analysis. So internally, we use mathematical convention. For plotting, we putting over transform the image to plot, and that is the way to have the least confusion, and it preserves the order of fast and low scans. And so if we are not consistent in any of these cases, tell us, because we definitely want to know and fix that. So consistency is, of course, important. So we'll talk about that in the next one. Okay, I cannot do that. Let's do this one. Let's go to the load file. So now that we know what an image looks like, we want to look at any of the different data that we can have. And here we now install with the first code cell. You can also run that on your own computer, and it installs everything for you that you don't have yet and need. So we are installing all the different packages, and the key one is here the PyTemlib. So that is a TM library of microscopy. It's built on top of SitPy, so that is internal memory representation of your data, or of our data, if you use that, your data. And the way to read it is a sci-fi reader, scientific file reader. Rama came up with that name, so it's very funny. So we were adopting it. Okay. By the way, microscopy has a hackathon, and that hackathon is on Friday, Eastern Standard Time, 3 to 5. So not convenient for Australians, I guess, but anyway, people are welcome to join. It's an open source thing. After we have downloaded everything, we can import these libraries. Matplotlib, I need to have that, of course, interactive. So we're using that one. In Google Colab, we have to add a few things. And it's mostly the file tools of PyTemlib that we are going to use here. I want to download a few files. I definitely would need feedback now if it doesn't work for anybody on Google Colab. If you're having it downloaded to your own computer, you have to download the example. The example data here from machine learning. Okay, so we are here. We have all of them. I got them. I wasn't sure whether it would be working, so okay. So key thing is you get data, you want to look at them. So it's just to screen them, of course, right? So there is a file tools, a file widget in file tools, and it just gives you this widget here where you can check that. I use that because that way file names and so on can be controlled. If you go on the left-hand side here and you click on this button, in Google Colabs. Okay, maybe I can do that too. Okay, then we have here our folders in Google Colab. And we have our example data. And we do the same thing in the widget. I select one, I select an image. Oh, super. Ah, yeah, okay. Made a mistake. So we select that. Not knowing your own software is a real problem, okay? Okay, so we select that as main. I forgot half of the how to use that. Okay, so we select that as main. And now we see what is loaded here in this pull down menu. And whatever we selected in this pull down menu is the selected data set here. All the data sets and any file can have several of them. If you do a spectrum image, for instance, in a DM3 file, DM4 as a digital micrograph file, then you have several of them. Do any kind of analysis. Of course, we want to put things together from different techniques, from different instruments even. So we select that and then we plot it. So you see the amount of code is minimal because everybody does it all the time. So it doesn't make any sense to make that very complicated. And any kind of, so let's add that. It doesn't have anything to do with it, so don't do that under normal circumstances. So now we have two different data sets here. The data sets are just Python dictionaries, so they have a key name and then whatever the name in the of the data set is. And if we select now that, we have a EEL spectrum here. Okay, so EELs. The reason why we need an interactive one is obvious, because you really want to look into what is in this spectrum, right? And the dynamic range makes it necessary to look at that with some flexibility. So everything is in this plot thing. Let's try another one. So here is, can add that. So now we have the stack of images, and even so in, so that's strontium titanate, just a stack of. Now we look at that in a moment. I'm not quite sure why it does not, it worked on my computer, but on this computer, the update of the image is not correct. However, we can do an average of those. Okay, we don't see much. Let's zoom in a little bit. So this is a single image and then the average one. Okay, so everything's there that we need. What kind of data set do we have? There are two ways to look at them in microscopy. One is with the print command. Then you get, okay, it's a SITPy data set, has a certain dimensions. It tells you the axis that you have in there. And if you just say data set, so that is the bottom part here, then then you get this nice graphics here, and that tells you that this data set is from a DASC, is on top of a DASC data set, DASC data format. And it tells you the dimensionality a little bit more graphically. The advantage of a DOS dataset is that you cannot run out of your memory on your own computer, and it's flexible and available for any kind of platforms that you can have. Any of the metadata is conserved. So I did the original data set, original metadata of this data set. Everything is converged, whether you want it or not, so you can delete it. The reason is we don't see any reason why that would be. However, in the data set, there are the relevant ones. So if we look for a different one, let's look at the EELS data set. We plot it, so we select it basically. Now we go down here and look at the metadata. Then you see collection and convergence angle are here, and we need them. And if you don't have them, no quantitative analysis of EELS is available or possible. And so you need that. You can save the file, of course. And then now we have saved really all the data sets that you collected. So you can analyze data set, you add them to this dictionary, and you're done. And you save all of that. The saving is done in PyNZ format, which is built on top of the HDF5 dataset, again available and on any computing platform. And if we save it, and we also have to close it, and we are done. I'm not sure whether you realize whether you can get in real trouble with this kind of technique here. Are we here with time? Okay, we're good in time. But I use dataset for any of my data, the same name. And so in a notebook, it's very critical to be very clear about your names. If dataset is actually relatively generic, so it is a generic thing within the notebook. So whatever dataset you're working on, and you can jump back and up as you want to, and the data sets, right? So over here are all generic. You change that by going to a different one. This is an especially boring one. Let's go to something. So if I select that as main, okay, this is a problem. Okay, I detected a bug here. Okay, so let's restart that part and go to EELS, and we select main. And then we have a different data set, right? So we have always the same name, but it might be different from whenever we did that. So we have to keep track of that ourselves. If we want to do something very specific, we have to make a specific name, and it should only be used in that specific code cell, so that we can only change it at some point in the notebook and not anywhere else. So in microscopy, we try to use the philosophy of the clean code. You can look it up. Python clean code will get you to various blog entries. So the names are important. Don't use just A, B, C or A1, A2. If you look at that kind of notebook if you're as forgetful as me after 2 weeks, then you already don't know what it means. So we're trying to do that as consistent as possible and the names as meaningful as possible. And we use the usual convention of Python with it. Yeah. These are my the data I provided. Let's wanted to do something else. What if you want to look at your own data? If you click this button over here, then it will make a code cell like this. And you run that. And if you have a Google account, so you're logged into, and you allow that, then nothing changed here. So we have to update that. So Google is a little bit behind with that. It will happen eventually. So no? Oh, here we are. So here we have now mounted our drive, my drive, not yours. So you can mount your own. My drive. So I upload all my data sets always up there. So this is the data from my lab course. Not sure what we did there. Okay. So, yield spectrum. Okay, let's try that. So we go here. Go back. Go to drive. My drive. No. My drive. We had this one here. Just the first one. I select that as main. And I plot it. Okay, very bad. Very good resolution. No intensity. That is a titanium dioxide one. You can see how nice and sharp this peak is. But in a lab course, of course, you do different ones. The key thing is whatever is uploaded to your Google Drive, you can directly access with the Google Colab without any kind of weird things, right? Okay, let's go to the last one. The adaptive Fourier filtering. So we do Fourier analysis. Okay. And I open it in Colab. And I don't have any data here because I opened a new instance, right? So we install all the different, say the PyTemlib with all the relevant packages that we need again. Okay, this is annoying, and if you do it on your computer only once, that is of course better. On the other hand, on Google Colab, if you give a lecture, and in your futures we will give lectures, all of you, or in your past, who knows who is on. So what we're gonna, it gives everybody the same, exactly the same environment, right? We're still waiting here. then we do again load that. That is actually a bit faster than on my computer, so that's nice. And we download 2 examples, only 2, which if we go here, now have our example data up here again on the left. My left and right is get a bit different here. If we look at the table of content, right? So we are in the open file thing. So let's look at that. We go to example data. Go to that first one. We select main. Okay, we don't make mistakes twice, right? So, okay, and we plot that image. This image is a zinc oxide nanoparticle on graphene with a lot of dirt. So in order to analyze any kind of image, the first thing you do is you look at the Fourier transformation. And all I needed for that is, again, I make a power spectrum and I plot it, right? So that's all we want to do. Let's zoom in a little bit. Okay. Let's make it a little bit brighter. In Matplotlib, this color bar is actually active, okay? I'm not sure whether everybody knows that, so we can just select that here. And it's bright. So what do we have here from the amorphous material? We have this background with some information missing, that are the so-called tone rings. We're gonna look into that and we'll see that I went actually to an underfocus, a term we learned, right? A bit more than usual. And these are related to the Bloch waves. So it's not really Bragg peaks, but the angles are the same, right? And in what we see is that all the noise is here in between these Bragg peaks. So it's, if you want to analyze only the structure, you want to separate the noise from the different, from the information. And the simplest way of doing that is with the Fourier transform. So what we do is we look for these Bragg spots. And we do that with a blob finder. Okay. SciPy, the scientific Python, has a blob finder, and it finds blobs. Again, we kind of. So in an image, your Bragg peaks are blobs. And now I have all of my blobs found. And now I can do something with that. So I can select, make a mask where only the blobs go through. And for reasons that we will see in a moment, we also need the center. And so we have 2 different things. So we have this low pass filter. The low pass filter is the center. So it's the low frequencies that are in the center. So we are selecting those. Okay. So that is the low pass filter. And did I see that? No, you don't. Oh, yes, you do. Okay. Can I not move that away? Okay. No. Okay. Let's get rid of it. And on the very end here, I have how big are the reflections. And that is in 1/nanometer. So how big of a spot do I take out? And so I go into the Fourier space, select that, and then I go back in real space, inverse Fourier transformation. Let's see what it did to our image. From, okay, I did it now in grayscale, whatever. But let's look here. Zinc oxide, very nice, right? So we can definitely do something with that. And if we zoom in to anywhere where the graphene is, we see actually now also the graphene. And most people stop there, but you shouldn't, because we learn things, right? First, we want to see what we really did. So as soon as you do the filtering and you publish that, people will do an inverse Fourier transform again, and they will see exactly what you did. So always a good idea to be very transparent. I did a Fourier filtering, and in this case, you can say a low pulse of this and that, many 1/nanometer, and the adaptive Fourier filtering, blah, blah, blah. So we can check now what the size of this inner particle here. How are we in time? Okay, that's good. Be good. So if we change, say, low pass filter to something very large, 1/nanometer, very important. So everything is in 1/nanometer on the images. There is a bit an inconsistency still, because I'm switching over to angstroms for being compatible with simulations, which always use angstroms. So it looks already a little bit less clean. And if we look in the Fourier transformation, we see exactly what we did. We just allowed much more noise, right? The noise in between here is what we allowed. If we do too little of that, 0.5, okay, then what we take out is a lot of the contrast. The low variation of the contrast is gone. And again, it's much easier to look at that in Fourier space. So looking in Fourier space on what you did and what you have is gives you a very clear image here. So we used only very little of the low variation of the contrast, and the rest we threw away. I find the best solution is usually to do something. Okay, we want to stop, of course, with something that makes a little bit of sense, something that is very close, where the contrast is about up to the first Bragg peak. Okay, so something like that. That looks very similar to the original image. And if we zoom in, we see we have contrast variations here that are still there. The noise is gone. And if we zoom in, we have, okay, not sure whether you can see that here on the scale. Maybe if we go back and move. Okay. think, if I remember, go in here. The graphene is much better preserved here. So it depends on what you want to do, what you want to see. We weren't interested in the graphene that much, but more on the contrast. And you can see what I did here. But the idea is, with this kind of method, you can directly say what you did. If you do the same thing in digital micrograph or any of the other imaging software, then you have to select all the dots. You have to make sure that you're really on it. It's very hard to determine the size of them, and so it's always a little bit awkward. But here, it's that's where it's a bit nicer. But we can go back and do more than that. We can look, where are these peaks? So it gives me now the distances. I calculate the distances here. So here I was first giving out the spots, and then here 1 over the norm from the linear algebra package of NumPy of the spots. You have to give an axis so that you get them all times 10. So now it's an angstrom. And yeah, then they're here. And we see the largest interatomic distances, or interplanes, I should say, interplane distances are 2.7, 2.4 in that order. So we have the first ones here. So we have another 2.7 here. The smallest one is around 1.4. So we reached about a resolution of 1.4 angstrom. We did that with an electron microscope that has a point resolution of 2.4 angstrom. So it means we are in the information limit here, not in the point resolution, but it still can be used, obviously. So, and then we add that filtered image to our data set, and we can save that. We can have a convenient tool to switch backwards and forwards between the different data sets, the original one, or the new one, the filtered one. Okay, so it has now all the information in here that is preserved under the metadata from your analysis, plus the image itself. And it's in a file, and so it's an HF5 file, so it shows you what's all in there. We close that file. And if you're going now to a new notebook and we want to use these data to do, it has also a name, a date set. So provenance is something in the analysis that got a little bit neglected. And so in microscopy, we really try to come up with good ways of keeping track on what we did to the data, when, in which order. Any idea of how to do it better, just talk to us, okay, please. So again, let's look at the filtered image. The plotting is a bit slow here. Okay, so this is the filtered image. This time we have it in the same color scheme, right? So the one I did last, that's the one I saved, right? So graphene, zinc oxide. but you can use that to be a little bit more creative. If I want to subtract two from each other, I can do that here. I want to subtract the Fourier filtered one from the original image. And that is a test in any image analysis you should do, right? Just to say and see, what did you throw away? What did we throw away? Well, at this level, it doesn't look right. We did throw anything away. We have to zoom in quite a bit. I'm trying to be about where I was before. And what I did throw away is mostly high frequency noise, right? Low frequencies are still there. This is a test that is really, really, really necessary for any kind of image analysis. Just subtract it so that you know what you took out that might be relevant and it doesn't get you in trouble, or might be the most interesting thing in your in your image or in your data. So that's it for today. I think we learned about the basics and the vocabulary that we're going to use. We learned how computer is storing the data in microscopy. We have the tools so that these data sets are easily managed. Let's try this. Okay, it's probably not gonna be doing very much, but you can, this is the same functionality as a NumPy array. So if you just add something, you get a ZipPy data set back, which you then can plot, and then you can make really long things out of that. If it is complex number like this one, it will automatically do that. Okay, so we learned that, and we did very simple, relative simple data analysis, but it's something that is basic and you should be doing any point in time to look at the Fourier analysis or Fourier power spectrum of your image. Okay, so it's the end of it. So let's see whether there are any more questions here. How do I do that? Go over here. Oh, did the video break down? Are we back?
No, it did not.
Okay, no, I see myself in the upper one, so I'm logged in twice. Okay, so yeah, STEM AFM. So the key things that we want to do is actually in microscopy, not only to do STEM AFM, but we want to do that for any kind of imaging, diffraction, or spectroscopy data, and any help is welcome. So the idea is, of course, the machine learning tools are the first thing, just different dimensionality of data, and so combining different techniques into that is key. So we do that here in this course for STEM. We do the same thing with AFM data. I do the same thing actually with DFT calculations. So we do the same thing. We get data out of that. We want to analyze them, and so it's supposed to be universal. Okay. Okay. Yep. Any more question? Everybody worn out here? Okay. Well, 3 new messages. Okay. Where are they? Here we are. Ah, okay. HF5 files and arrays. So it's a Dask arrays that we use there. And on top of those, we have different attributes. In the attributes are like, dimensionality, units of the axis, the scale of the axis, that kind of stuff. That is your data. With the metadata that make it useful, right? So immediately recognize if an image has light years on it, it must be something in from a telescope, while from a microscope, it probably has nanometer or micrometer on there, different scales. So that is what's in the memory, or kind of in the memory with the Dask array. So it's buffered in the memory. If you run out of normal memory, it puts part of it on the disk and it chops it up so that it has fast access to them. So in the HF5 file, it's an HDF5 file. That is when you store it. So you store it and then you send it to the supercomputer center, do your machine learning on it, send it back, plot it in your notebook, blah, blah, blah. That is so really stored on the disk. So that are the two things. And the data format we use there is called PyNZ. And Rama will talk more about this next week on Tuesday. That's at least is what I was told. Let's see where it's going. The idea is to make it as universal and as flexible as possible and have all the relevant data in there. So, okay. Yeah, I don't know where this convention comes from. I think the first okay, hold on. I do this one first here. We have a new question here. The convention comes, I think. So here it's the same thing, right? So we start here. So I think it comes from writing. The first SEMs. So SEMs were the first scanning microscopes. Out there, we start on the top left, and I think it comes from reading and writing. If it would have been invented in Israel, we probably would go from here to here, or in an Arabic country. So there might be other cultures that do it differently, whatever. But yeah, so that is a convention, and so you use something. Some of the conventions don't make sense anymore, obviously, but okay. So under Windows, what you have to do is, why don't we do it? I'm not sure. Example data. You can actually download the raw data here on this side. An alternative would be to go and download all the notebooks at once with zip, or if you want to see what's going on and what's updated, say GitHub. Desktop is actually a very convenient way to keep track of things. Okay, yeah, I haven't uploaded this one yet for you guys. So that tells you what you changed and what you want to upload to GitHub, or vice versa. So, if anything changes, you can say fetch origin, and it will download the newest versions onto your computer, and you're always up to date. So I think that is a very convenient way of doing that. Okay, let's go over here again. Where am I? Many mice. Okay. So under Windows, you have to do that because you have to have it on your computer, or yeah. So that's the idea behind it. Again, don't waste your time with our example data. If you want to do it later at home, use your own. Just load them up. If there's really a problem, make an issue in microscopy. Okay, where's microscopy? You see, I've searched it a lot because I cannot remember where. Lazy to do that. So in microscopy, all the different ones that we are going over in this lecture series. Here's PyTemlib. That's the one we were using. And again, you have some notebooks here to use them. You want to know more about the formats. So here is the ZipPy format. Okay. And we have our documentation for that as well, for each of them. Okay. Okay. More answers and was asked. Okay, typical professor, sorry. Okay. Anybody else? Okay. Well, that's it from me then, if there's no more question. So I'll see you all on Tuesday, where we do EELS, electron energy loss spectroscopy, low loss and core loss, quantitatively. That's the key. And again, remember all your different settings. Everybody have a nice weekend. I say so too. How do I log out here? I'm not having a mouse. Here we go. Bye.